So you're listening to Data Skeptic. And you can imagine that people like you are also listening to Data Skeptic. Would you like your message to reach them or your company's message to reach them? Why not consider advertising with us? Send your inquiries to advertising@dataskeptic.com. Who is ready to go straight to a computer doctor? I definitely am, but I know I'm an outlier in that. Most of us don't yet trust our health and our bodies, or at least the review of the diagnostics on those things, to a machine. Perhaps for good reason. Last week on the show, we learned about ObjectNet, the computer vision corpus designed to be more of a capture of the real world after the observation that a lot of the popular data sets are intrinsically biased. It's the dirty little secret of computer vision that, with all the high accuracy scores, generalization to the real world still is a problem. Another problem is the ability to fool these systems, as we discussed with Ang Win quite some time ago here on Data Skeptic. These adversarial attacks that can be performed on the neural networks. And at first I wrote that off, said, well, you've got to have the weights of the other network. That's paramount to having a breach, almost, or a security leaks. How did someone get your model? Yet we've otherwise learned that models can be stolen from APIs. Knowledge of the training dataset can often let us know already what baked-in biases or potential for adversarial attacks might be available. Transfer learning makes that even worse. And there's been quite a bit of research. To be frank, I haven't read all of it yet, but it seems to be the case that you can do adversarial attacks quite effectively without those weights in a lot of situations. While we're criticizing, let's throw in the ever-popular accusation that neural networks are black boxes. We have literally no idea whatsoever how these things work. That's rather blatant clickbait. Scientists may not totally understand what's at the depths of the oceans, but they're not blind. Neither are machine learning practitioners. We're building the tools of interpretability. What do we need to do to sufficiently explain the decision-making process of these models at a higher level language? One not involving tensor multiplication. Yet I've recently learned that even some of those interpretability tools can be fooled. An adversarial attack can be used to generate what appears to be a convincing explanation, although one that really isn't a generalized explanation for the operations of that model. But therein actually lies something kind of insightful. It reminded me of early math courses. You study as best as you can for the test. You show up, the first page is all easy answers, then a couple of difficult ones, and then out of the blue, as that test is winding up, can you believe what this teacher did? They snuck in an example that we didn't really go over in class. What do you do when x is negative? We didn't talk about that. Teacher's trying to trick me. No, teacher's giving you a adversarial example, and the way in which you respond is going to be quite insightful as to whether or not you memorize the rote performance of a few actions or you generalize the technique. Perhaps the true path to model interpretability is watching how our systems get fooled. Welcome to Data Skeptic Interpretability, a podcast about computer vision, adversarial attacks, and model interpretability. Today on the show, I've got Walt Woods, who joins us to discuss his paper, Adversarial Explanations, for understanding image classification decisions and improved neural network robustness. This is what inspired the introduction. It broadened some of the ways I think about neural networks. I'm excited to get into that interview right after the break. Thanks to this week's sponsor, the 2020 Gartner Data and Analytics Summit. While this event is next year, in Grapevine, Texas, March 23rd through 26th, now is the time to act. You can save $350 with my early bird code. Those of you traveling on the company dime, keep in mind that your boss may have a budget for events and travel and this sort of thing, and if he or she doesn't use that up, they might lose it. The agenda has gone up on the web. 2 keynotes that caught my eye were Lee McMullen, speaking on creating a culture that is ready for AI, and Dr. Hannah Fry, who I love. She's on more or less all the time. I read one of her books. She's great. Professor, mathematician, author. That's just the tip of the iceberg across the 8 tracks they're offering. Visit gartner.com/US/data. That's Gartner, GARTNER.com/US/data. There, enter the discount code, all caps, no spaces, Data Skeptic.
I'm Walt Woods, and I am currently a research engineer for Galois Inc. in Portland, Oregon.
And what do you do there?
So Galois is a bit of an R&D lab that focuses on trust in critical systems. And so right now I'm working on a couple of projects, one of which deals with kind of, PDF is a very broad spec. There's a lot of files that fit in that, and there are a lot of parsers for it. And so basically, because you have multiple interpretations of the spec, can you then reason about the overarching security properties as people kind of add on to this language? And can you track how exploits grow in that space along those lines? And then some malware evolution stuff.
And looking through your Google Scholar record, you're pretty diverse in the topics you've published on. In addition to the computer vision paper we're going to discuss today, could you give me a sense of where the breadth and scope of your research interest comes from?
Sure. So I joined academia after being a senior software developer for a few years because I wanted to work on more difficult problems, basically. And I had dabbled with machine learning and neural networks a fair amount, in a high school making games. Oh, hey, neural networks, that's a way to avoid hand coding an AI agent, right? I suppose that when I joined grad school, I figured that what was holding the field back was the hardware, that there wasn't fast enough ways of simulating large enough networks. So I actually went to grad school for ECE and did some work on accelerating what's called sparse coding algorithms. So there's some biological research, right, that what your eye is doing is breaking down the visual scene that you're looking at into these kind of salient components, and then it's just a composition of those components that actually get processed by the rest of your brain and say, hey, maybe I should dodge that car driving towards me. And so sparse coding is basically a mathematical means of approximating, here's a bunch of raw pixel data, let's turn that into, higher level components. So it dealt with some circuits for that. And then the computer vision stuff, which I was really excited about because interpretability. And I kind of got back on that because it was rather apparent that hardware was not what was holding these algorithms back. Watching the GPU boom, as it were, and seeing Google harvest, thousands of GPUs to train on ever larger data sets, and seeing that they're eking out a few more percentage points on tasks like ImageNet, but definitely not solving the problem in a way. And that's part of what makes adversarial examples so interesting too, right? Is that it doesn't change the semantic content of the image, but the interpretation is completely different.
So, on the show previously, we've covered adversarial attacks, and I'll put some links in the show notes, maybe even to my early recording with Ang Win, who was one of the early publishers. I guess their claim to fame was their adversarial images weren't just noise gradients, they actually kind of looked like things. So, I think they even won some art contests with these adversarial examples they had. So, I imagine the listeners get that part.
Question, is that related to the deep dream stuff then, or which thread are they pulling?
So I think that's more towards the root of it all. They are one offshoot that was saying, hey, we can design other variants of adversarial images. They aren't just these purely kind of Gaussian noise things. We can do them in other more interesting ways. I guess all of this is my long explanation to say we've talked a lot about adversarial attacks on the show, but we've never had the phrase an adversarial explanation. What's that all about?
Yeah, so that was kind of a fun term to put together. But, if you think from a person point of view, if you're looking at a picture of a bus, there's a series of image transformations you can apply that will eventually turn that picture of a bus into a picture of, say, a frog. And if you think of that as a spectrum, basically, right? If you take a picture of a frog and subtract a picture of a bus, that's kind of a one-shot hop to go from the bus to frog. But as you turn down the magnitude of that perturbation, eventually there's going to be a hazy gray area in the middle where you're not sure if it's a bus or a frog. And so it's kind of interesting that that didn't happen in machine learning applications, and that kind of bothered me. This work actually grew out of the idea that we would stick an intermediate layer in the neural network and do some heat mapping on the intermediate, because attention networks had become a thing. So it's clear that if you look at just the input pixels, you could make sort of a heat map. So then that got us thinking, well, maybe you can make a heat map of some of the intermediate steps and pull something interesting out. But what became clear pretty quick is a heat map for a frog and a bus might look the same from certain angles, and B, it still was unstable, right? Adversarial examples kind of highlight how unstable neural networks are. And even if you have a really convincing explanation, a really convincing heat map, if you can perturb that image ever so slightly and get a completely different result, well, how much was that explanation really telling you? So all that's kind of a noodly way of saying that the recognition that current explanation techniques were kind of fragile in the face of these adversarial explanations, coupled with the fact that, in the salient domain world and what we think of looking at a picture, is that a frog, is that a bus, there should be more of an intermediate ground between the two images and it's borderline sensible. That seemed like a domain that was really lacking. And so set out to try to develop a transformation that would at least approximate that with neural networks.
And do you think this is a property that's exclusive to computer vision, or is this just the one place you happen to be battling with it?
No, definitely not. It shows up in a lot of machine learning. Tabular data applications get this too, somewhat. I think one of the papers I cited for the Adversarial Explanations paper talks about tabular data and how you can generate adversarial examples on that too. And it kind of boils down to the same idea where, if you have a truly robust classifier that, if you put some input in, always gives you the correct semantically significant output, then you would expect that when that output changes, if you look at the changed input, it should reflect that semantic change. And so most of my work focused on the visual aspect, but the hope down the line would be to extend it to tabular. The method was derived specifically to be pretty general.
And then I didn't get out the full title. It's Adversarial Explanations for Understanding Image Classification Decisions and Improved Neural Network Robustness. Before I guess we get into the core contributions, you have a pretty well-cited and well-researched related work session. Could you hit on some of the highlights? Bring us up to speed to where your contributions begin.
There's been a lot of great related work in adversarial examples. One of my favorites is this Lab 6 work by Atelier et al. Apologies, that's a mispronunciation. But they actually took the idea of adversarial examples into the kind of, I believe, 3D printed a model of a turtle and painted it in a certain way so that if you hold it up to different camera angles, it always shows up as a rifle in Google's object detection thing. I really like that as an example that, this is more than just a minor image manipulation problem. It's actually highlights an issue with the way neural network vision applications process data. So Alexander Madry et al. Has a good body of work on what's called adversarial training. So Atelier et al. Kind of showed, hey, this is a real thing. We can derive real world representations that from a variety of angles actually cause adversarial effects if you're using like a phone camera. And so Madry et al.'s theory was kind of, if you look at what these adversarial perturbations are and you just build them into the net training cycle, maybe the problem will stamp itself out. And they actually show a fair amount of the initial robustness results that have held up over time. There have been some other denoising approaches that have been proposed, but a lot of those rely on assumptions that, at least if you assume you can see the weights for the network, don't hold up. You can basically always derive an adversarial attack that's still low magnitude, whereas the Madry et al. Work produces more robust networks.
Yeah, those examples like the turtle and the rifle are almost terrifying to me in the sense that I see so many positive case examples of computer vision working well. Like YOLO is such a great example of that. Like, wow, real time processing, getting all these objects correct. One could easily build a great deal of confidence that computer vision is approaching a solved problem. But then you tell me this painting turned sideways, suddenly a rifle. How are we to reconcile this cognitive dissonance?
Yeah, it's very alarming, especially if you consider it. For a brief moment, I was touching on some airport security applications. And I mean, just imagine there, right? If you just design a certain material that, completely hides basically what this object actually is, an airport scanner. I mean, that's a very real thing that could happen with current machine learning tech. This work was fun to work on for two reasons. One, it shows you kind of what the model's looking at, right? The idea of adversarial explanations is that biases in the training data actually show up and you can see, it's keying on this feature, which maybe is present in all the training data, but doesn't generalize to the object class that it's actually trying to detect. B, the techniques in the paper actually result in a more robust network. And so I think that there's a lot more progress to be made in this space where you can make a machine learning model that acts more like you or I would when presented with adversarial images, where we make a more reasonable gradation of this bus is turning into a frog, or this turtle into a rifle. And so basically, I guess, stabilizing the models almost seems like an important step in addressing that particular issue.
And do you have maybe a tangible example of what it means for the training data to have one of those biases that shows up?
Yeah, I don't know if you're familiar with Rubaiyat-al-'s Lime work.
Of course, yeah, we're going to have him on the show in a couple of weeks, actually.
Well, that's fantastic. So I feel like they had a really good example of this where I want to say they trained a bunch of pictures of a husky and there was always snow in the background. And basically, if you then showed that classifier an image of anything with snow in it, snow was the dominant feature where even though they were trying to get the network to key on the husky, it actually ended up keying on the snow. There's also, I don't have a citation on hand, but I know some researchers have done work on like racial profiling in police systems. And that's another place where this sort of bias can creep in a scary way, where you might have, the number of convictions to date fitting a certain profile, which has nothing to do with the crime at all. And then you can make certain disturbing statistical correlations there that aren't necessarily indicative of the underlying thing that you're actually trying to classify.
Yeah, very pointed example, also alarming. With that in mind, I definitely see the value in why we'd want better explanations. I know we haven't touched on the methodological choices yet, but from sort of an end to end point of view, if someone were to be benefiting from your contributions and the work described in this paper, how much better of explanations do they get? What sort of added interpretability can they expect to gain from the experience?
That's a tough question to answer for a couple reasons. One is that a lot of the output is qualitatively different, right? And if you look at the appendix of this work, there are a lot of examples showing different transformations and comparing, again, the Madrigal network. If you just do adversarial training and then do some of the explanation transforms I talk about, you get things that look kind of like the target class. So, like in figure S5b on the paper, there's this little picture of a dog as input, and the eighth column shows it turning into a horse. And, if you look at just an adversarially trained network, qualitatively, it's difficult to see a horse. You can kind of see that it's getting some maybe red leg wraps in the lower right corner or whatever. And then if you look at the rows below that with our method, you get something that looks holistically like a horse. So from a qualitative point of view, I would say that this paper significantly improved the quality of explanations you get out of networks over previous work. The methodology, we attempt to quantify that too. There's this concept of back to random accuracy robustness area. So do you want me to get into that methodology a bit, I guess, and compare that to prior work?
Yeah, I'd love to, because everyone will know techniques like accuracy and F1 score and these sorts of things, which are wonderful statistical tools. But I guess your qualitative tool has more rigor than most do in a way, and that's kind of interesting.
Well, that's the hope, right? But you always want the number to go up when the quality of the results goes up. If you're doing that, as far as image quality goes, you're doing well. So I guess I'll start by talking about the accuracy robustness area a little bit. Early in this work, I had this basic idea of kind of this Lipschitz constraint, and it seemed like the results were good. So let's compare it to other related work. And looking at the adversarial example literature, what you find is a lot of people say our classifier, on CFAR 10 gets, say, 92% accuracy on a clean data and 60% accuracy when it's under attack by an adversary. And the problem with reporting results that way is that 62% accuracy under what conditions, right? What type of adversary are you using? How large of a perturbation are they allowed to make? What do the resulting images actually look like? All that information isn't really rolled into that 62% single number. So, looking at precision recall curves basically for inspiration, where if you're doing this binary classification problem, you want to weight false negatives against false positives and look at how your classifier does with a number of different thresholds. If you plot that ROC curve and then you take the area under it, you get kind of summary behavior rather than behavior with one given threshold. So the idea with accuracy robustness area is to do an analog of that, where rather than we're going to report the accuracy of our model against one specific adversary that is allowed a perturbation of, 10% of the overall image magnitude. Let's look at how the classifier's accuracy degrades against adversaries allowed to make increasingly large perturbations to the image. Because again, back to the bust a frog example, at some amount of perturbation, you want your classifier to change, right? Even the perfectly robust classifier should break down at some point. And so, kind of looking at the behavior of how, as you increase the size of perturbation allowed, looking at how the classifier's accuracy falls, if you take the area under that curve, that's what accuracy robustness area is supposed to capture. So that's accuracy robustness area. And so if you have a data set like CFAR that has two highly related classes, a truck and a car are the example I use in the paper. Those share a lot of features, right? They're both vehicles. They both have a lot of kind of square edges. There are differences. There's a reason we call a truck and a car, but they're very highly related classes. And so when we were testing our network modifications against the Madrigal modifications, the attack ARA, where you just measure the top one accuracy of that classifier degrading against an adversary, wasn't actually producing numbers that I felt correlated well with the qualitative change in the explanation. So that's what led to this thought experiment about cars and trucks being highly related classes, where how do you measure? In an accuracy sense, those will always be close together. You almost expect that a smaller magnitude perturbation is going to turn a truck into a car than versus a truck into a frog. Okay? Making a truck into a frog should take a higher magnitude change in the pixel set. And so that's where this better than random ARA was conceived, where what if rather than just measuring the adversary's distance to, hey, let's make the classifier wrong, instead, let's measure the perturbation size needed to transform the classifier's prediction back to a random chance prediction. So if you have 10 classes and the initial classifier confidence is 60% it's a car, let's go from 60% all the way down to 10%. And that number, the BTR ARA, or better than random ARA, correlates very well, in my opinion, with the explanation quality you get out of the model. One hope, honestly, going forward is I would be super excited to see the accuracy robustness area ideas coming out of some of the tests of subsequent work, because I feel like it's really important to characterize the behavior of a classifier against a whole range of adversaries rather than just reporting one accuracy number at a certain fixed perturbation.
Yeah, absolutely. Do you have any thoughts on the reproducible process for how we make that happen? A lot of the vanilla statistics like an F1 score, most of the popular machine learning libraries have the tooling built in, whether it's sklearn or whatever. These are new ideas that aren't yet in those libraries. How can they be popularized?
Yeah, that's a great question. And I suppose getting an implementation into one of those libraries would be a good start. But this paper does have code attached. It's honestly a pretty simple algorithm. You just sample 1,000 in this case, images, and you measure basically, how far an adversary would have to go to break each of those images. And you build a curve and do some stats. So there's code for handling that attached to this paper. Maybe I should put in a pull request to PyTorch or something for getting this sort of evaluation easier to access. Because you're right, that is a barrier to entry. At the end of the day, everyone's their heads in the sand focused so much on what they're researching that if you come across a mention of another evaluation criteria, you're just going to skip over it if you can't find a readily accessible means of implementing it.
Yeah, similar question when it comes to the half-Hubbard rectified linear unit, which first of all I should ask you to define, but given its importance in the contribution, how can one get that maybe into TensorFlow or wherever they might be using it?
It's a real small change. I think it's like 10 lines of code or something to implement the half-Hubbard rectified linear unit.
Not at all difficult methods to pick up and start using.
No, maybe that's the better point here, is that I don't know how much research works this way, but this research, at least, one of the two main outcomes, the Lipschitz constraint and the half-Hubbard rectified linear unit, main outcomes in terms of modifying models, both reduced to pretty simple implementations. And you can see that in the code attached to the paper. They're both very small changes to the training process or your activation module that really make a significant difference in the results you're going to see in terms of explanation quality.
Yeah, there's something that kind of interesting for me in how something that takes so few lines of code and is an arithmetic process, I guess if you break it all down, that can have this big consequence on this more abstract idea in the same way, I don't know, if we change the chessboard from its current shape to +1 squares all around it, the whole game would probably be very different. What's the intuition that got you to come up with that insight and then think to try that instead of the myriad of other functions you might have tried?
I forget who said it, but there's a quip floating around somewhere about gradient descent via grad student. So, in a sense, the way this Lipschitz idea came about, again, I was playing with other methods of explaining a model and trying to come up with. So Lime, if you look at prior explanation techniques, a lot, and attention models, there's some great attention model work as well. But if you look at those, they're all focused on the generation of a heat map. And if you have two things that have a similar silhouette, the heat map's not going to really tell you much about that. And so the original thing that I was setting out to do, in a sense, was come up with some way of producing high definition, full color explanations that would actually show you the rich features that the network's keying on. And adversarial examples were a natural problem for that, because you could make a small color space change and end up with a completely different output. And so basically, there have been a lot of theories about why adversarial examples are such a thing. And one of those theories is that neural networks are too linear. If you then measure basically the rate of change of the output of the network with respect to the input, you can see that, yeah, the output changes a ton when the inputs change only a little, which kind of reinforces that view of adversarial examples. I don't necessarily prescribe to that view as an overall explanation for the phenomenon, but I think it's an interesting thought experiment. The Lipschitz constraint is what you get when you minimize that quantity, right? When you minimize the rate of change of the output given the input. And so it basically naturally fell out of that kind of poking at how can we get a full color explanation to pop out when full color changes change the output of the network too much. If you backtrack that, well, what's a way to measure how much the output's going to change when you change the input? In this case, it's the derivative, basically, and then applying the Lipschitz constraint naturally minimizes that, and it turns out it works very well. There is a fair amount of prior work on layer-wise optimization or constraint of the Lipschitz constraint. It just really turns out that end-to-end made all the difference, in this case at least.
So the paper walks through some of the steps you guys took, beginning with CFAR 10, doing some training on that data set, and then going on to generalize to others like the ever-popular ImageNet and COCO and whatnot. Can you talk a little bit about how you saw the work evolve when moving into other data sets and domains?
Going from MNIST to CFAR, MNIST being, of course, the ever-popular black and white digit data set, MNIST to CFAR is a really big step. You're getting a much higher resolution image, well, a somewhat higher resolution image. You're getting full color, and the diversity of the classes, there are backgrounds included, right? There's a lot of entropy in each image, basically, that your machine learning algorithm has to filter out. And so there are a lot of algorithms that can show promise on MNIST, but don't scale really well to CFAR. In contrast, when you're scaling from CFAR to ImageNet, the semantic content of the images are basically the same. If I'm not mistaken, CFAR is a scaled down version of the same data, basically, that makes the ImageNet data set. And so the main issue with going to ImageNet is the number of outputs, right? Going from 10 output classes to 1,000 output classes. And where that, if I'm being frank, basically I got lucky. What happened there is when you stabilize the output, as the Lipschitz constraint does, it doesn't matter as much if you're dealing with 10 outputs or 1,000, because you're stabilizing all of them relative to one another. To pivot, actually, what was really interesting is going from CFAR 10 and ImageNet to the Japanese Society of Radiological Technicians dataset, the lung nodule dataset. And what's so fascinating about that is you only get, I think it's 247 images total of full chest x-rays, and I want to say 100 some of those actually have nodules. But it's still a high definition data set. And so basically dealing with still a high dimensionality data set where you don't have as many examples of each class. That was a really interesting and kind of difficult to wrangle transition. So part of the paper discusses an adaptive technique, right, for figuring out how strong this Lipschitz constraint should be so that you still get good accuracy out of the classifier. It's just robust accuracy. And when you have so many fewer examples of each class, that balance is a lot harder to do with a fixed scalar. So the adaptive technique, I think, really came out of dealing with that JSRT data set.
So this research really leaves off a couple of possible points you could follow up on it. Could you talk about a few of the directions that you yourself or maybe you hope others may head following up on this?
Yes. There are two follow up aspects that I personally am super excited to see. One, and you touched on this a little earlier, is extending it to domains other than just images. Again, the technique's super generalizable. It should work just fine on audio data, in some encoding space at least, and it should work just fine on tabular data and or word embeddings or something along those lines. And I think it would be really interesting to see how it would end up actually applying to those data formats and what the explanations would look like, and if any algorithmic changes would be needed to get it working. The second aspect that I'm very excited to see is, I'm actually a little annoyed at this. It's always, if you'd had more time, you would like to see a better version of the research, because a lot of the feedback I've gotten on this work mentions, and rightfully so, the reduction in accuracy on clean data that these robust classifiers get. And it's very much an open topic in the literature of, can you make a classifier that both is accurate and is robust? And what is so fascinating to me about this work, and the thread that I would really like to pull at, is why does the training loss, in a classification sense, never reach zero? I think it's so interesting that neural networks, which have so many parameters, and if you're not applying this sort of regularization, and it's worth pointing out, it turned out in the course of the paper that no other regularization like shape drop or dropout or anything like that was applied in this work. Just the ResNet architecture with the Lipschitz constraint was enough. If you take a base model and apply it to especially a small data set like CFAR10, you expect your final training loss to be very close to zero. You expect to have almost 100% accuracy on training data, and then it doesn't generalize as well over to evaluation data. But in this case, there's something about the combination of the regularization constraint, the Lipschitz constraint, and maybe the model architecture. Maybe there's a better activation function than the half-Huber. I'm not sure, but you would imagine that there should be some combination which allows for that overfitting on the training data. And I think that would be fascinating to see, because in my results, the loss on the training data and the evaluation data in a classification sense are basically identical, right? I end up with, so the most robust networks have around 69% classification accuracy on CFAR10, but that's both training and evaluation. And it's just not expected that you would see that, or at least it surprised me. I think that there's work to be done there to explain why the parameters for the network are getting locked up in that way, basically. And if you can unlock them, then you might recover that accuracy while retaining the robustness gains.
Do you think that's kind of a formal trade-off we're going to encounter? The way we have bias variance, it's robustness accuracy. Is it that sort of level of formality or just more of a heuristic, I guess?
I think that's what a lot of the field is pitching. I think that the most robust classifier you can imagine for, say, school buses is always going to predict a school bus. If you have a classifier that never changes its decision, that is by definition the most robust classifier you can come up with. But it's not very useful, right? And so clearly in the limit, there is some amount of trade-off there. But I don't think we're close to it now. I think there's a lot of headspace to grow into in getting networks that are both accurate and robust. And frankly, even the Madry et al. Work on adversarial training, I believe that they drop 7 points of accuracy, maybe down to 90 or something percent accuracy, and they get a significant gain in this accuracy ARA metric that the paper talks about compared to the base classifier. And so extrapolating from there, one's got to imagine it can be pushed out even further without sacrificing accuracy, or as much accuracy as this work sacrificed.
So robustness is largely about dealing with those biases due to the training sample we touched on earlier. In that regard, how will some of these methods help in getting more generalizable models, models that'll transfer to domains it hasn't seen yet?
Super interesting question. I think because you would expect, right, that in this adversarial explanation work, it's visually apparent that the classification network gets a pretty good idea of what objects it's looking at. It kind of understands at least the rough outline of what a horse should be, and yet it doesn't generalize as well. And what's interesting to me is that adversarial examples on non-robust networks are transferable, right? They pick out noise patterns that are independent of the initialization of the network, meaning that you can initialize a bunch of different networks and they'll all be susceptible to the same noise pattern in the input. And what that tells me is that the popcorn noise adversarial example that you traditionally see is a feature in the data set, right? It is a bias that actually is there. And shockingly, it generalizes really well. So it does indicate that there's kind of something missing from current robustness techniques because we're not seeing more generalizable accuracy out of those models, even though the features they're keying in on are, lower frequency, more saliently observable in a sense.
Very interesting, yeah. Well, first, tell us where to find the code. I'm sure at least a few listeners are going to want to give that a spin for themselves. And if they wanted to maybe reach out and discuss the work, what's a great place to get in touch with you if you're open to it?
Sure. So the code is on GitHub. It's at wwoods/adversarial-explanations-cfar. Feel free, if anyone's interested in chatting about adversarial explanations or really anything on model interpretability and explanations, I'd be delighted to receive an email. The email's in the paper. It's woods@pdx.edu.
Excellent. Well, Walt, thanks again for taking your time to come on the show and discuss your work with us.
Yeah, thanks for having me. Had a lot of fun.
Thanks for listening to Data Skeptic Interpretability. Our guest today was Walt Woods. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. Our theme song is Number 5 by Big D and the Kids Table, which is off a split 7-inch with Lounge, not off Shot by Lamy like YouTube would have you believe. But in any event, last but not least, I've been your host, Kyle Polich.